Bienvenidos a la primera sesión del ciclo de primavera de seminarios de la facultad. Hoy tenemos con nosotros una persona la cual es una satisfacción presentar, porque primero porque es una persona, digamos, de una excelente trayectoria y muy competente, y luego porque es una persona de la casa que estudia aquí en la carrera, fue compañera de nuestro compañero Teo haciendo el doctorado en una universidad de desarrollo del tema de la Universidad de Chicago, que ya lo sabréis, pero si no lo sabéis...
San Diego.
La Universidad de California, no de San Diego. Universidad de California, San Diego.
San Diego, perfecto. Que por si no lo sabéis, es una universidad de un considerable prestigio. Actualmente está en la Universidad de California Riverside.
Sí,
está perfecto, ¿vale? Bien, entonces, ella es experta en econometría, el desarrollo de métodos econométricos y su aplicación en distintos campos, sectores como mercados financieros, volatilidad, predicción. Es presidenta electa de la International Institute of Forecasters. Está bien, ¿no?
Sí, está bien elect.
Y pues, ha publicado en las mejores revistas, Journal of Econometrics, Journal of Business and Economic Statistics, Journal of Econometrics y otras muchas. Es una persona, digamos, que no hay más que ver su currículum para darse cuenta que es una persona de una gran solidez, que ha sido merecedora de varios premios a su trayectoria. Su investigación es financiada por instituciones muy reconocidas. Y bueno, también es associate editor del International Journal of Forecasting. Bueno, no voy a entrar en muchos detalles para no, digamos, avergonzarla. Y bueno, seguramente que ella nos va a demostrar en su presentación el nivel de competencia que tiene, ¿de acuerdo? Bueno, pues le doy la palabra a ella, luego tenemos a Felipe que la descansa. Y los que guardáis, los que tenéis obligación de asistir, tenéis la hojita de firmas para que dé constancia, que aparte de la satisfacción de la presentación, también el reconocimiento. Muchas gracias.
Muchas gracias, Paco. Bueno, pues como Paco ha dicho, siempre es un placer visitar Madrid y en particular mi alma mater. Yo me gradué mi licenciatura desde aquí, me gradué en el 69, estábamos recordando estas fechas durante la comida y tengo la sensación de ser viejísima, pero los conocimientos que adquirí en esta universidad me valieron para mucho a lo largo de muchos años. Yo tengo una deuda con esta institución. Me voy a cambiar al inglés porque si intento dar un seminario en español y en inglés no nos va a entender nadie, ni yo misma. All right. So I was told that I have to prepare a general lecture. So what I would like to do is to give you a general view of what forecasters are doing these days, and in particular to present some of the tools that my students and I have been developing for several years. In my way to California just a few weeks back, I was reading The Economist. And you know, The Economist is famous because it's very sarcastic in the way that they write their own articles. So I was reading this article, Free Exchange and Mere Feet, in January 9th, and oops, did I do something? Ah, que no se puede tocar la. Okay.
¿Y ahora hacemos para allí arriba? Las dos flechitas arriba.
La que no se puede tocar, ok, bien. Vale, ok. Okay, so then this gives you a sense of the perception that forecasters have in our society. The only function of economic forecasting is to make astrology look respectable. And the quote is by John Kenneth Galbraith, a former, well, I think it's the late John Kenneth Galbraith, a very famous professor at Harvard University. So the thrust of this talk is basically to go against this sentence. Why they are looking at us from that point of view, and basically what I want to do here is to mount the case against this type of comments. So I'm going to start by...
No funciona tampoco. Que toque la Sacando la pantalla.
No, no, no.
No, okay. Okay.
Una vez nada más.
The end.
Hay que moverlo así, ¿eh?
Sí.
Prueba a verlo con el mando.
All right. Okay. Let's. Okay. Now it goes. All right. So I'm going to start from the very beginning. So then we put our hat of forecasters. What do we face and how do we solve the problems that we encounter all along? So the very basic point here is to know the data, economic and financial data. And for this audience over here, I don't have to say what do we mean when we say about economic and financial data. So most of you over here have dealt with any of this information at some point in your life as an economist. So then economic data, mainly macroeconomic data, we have gross domestic product, industrial production, inflation, unemployment rate, household income, so on and so forth. Financial data, what do we have? Stock prices, exchange rates, mortgage rates, interest, options, and derivatives, commodity prices, bond prices, etc. Right? So this is the data that we economists we work with, and the very first point here is to understand what the data look like. So here you have two examples. This part over here is a gross domestic product in the United States. This is the growth rate. This is quarterly data. The growth rate is a quarterly growth rate. And on this other side, you have the S&P 500 index. This is the index itself. And this is the returns, the changes, and the frequency over here is daily. So when we look at this type of data, what do we observe? That if we stop over here and say, well, these two series are very, very similar. The data is before the crisis, 2005, and it goes 10 years, up to 2015. But when you look at the growth rate of GDP versus the growth rate of the S&P 500, these time series, they look very, very different. So then what are we facing? This is the object that we need to model, and this is the object from which we have to extract a forecast. So just to give you a sense of what I mean by what are the characteristics of this data, so here you have, again, this is not by any means an exhaustive list, but what you have is that macro data is low frequency. In financial data, we have high frequency, the highest frequency that you can imagine. You collect economic data mainly through surveys, but the financial data, everything is done through computers, so we have very clear and transparent electronic records. In macro data, you deal with aggregates. In financial data, we have individual transactions if we want. When you collect economic data, normally you are working with different vintages because to make a forecast of GDP is something that we want to do it very quickly, but we don't have the most updated data, so then normally you are basing your forecast in the last vintage that is available to you. In contrast, financial data, you have information on real time. Economic data tends to be much smoother. Financial data is very noisy. In macro data, it's very easy to spot the trends. In financial data, the trends are not so clear. We worry a lot about volatility. In economic data, the question of a forecaster is when we have the turning points, when we move from a recession to good times or good times to bad times. In financial data, we have a lot of outliers and we have a lot of clusters. In macro data, we have to have, many of the series have momentum, so because they are very smooth series. In financial data, you have a fast, quick, mean reverting behavior. We worry in macro data that we have breaks, but in financial data, we worry about jumps. Macroeconomists, they work a lot with normal densities, or mixture of normal densities, but the financial analyst doesn't want normality, wants fat tails, wants asymmetry. So what I'm trying to say is that this thing that we call economic forecasting is a big bucket. And depending on the data that you are looking at, the characteristics are very, very different. So just this gives us a sense that in order to have a sound forecast, we have a very complex problem at hand, because if you worry about all these features of these data, these features have to be somehow built up into your models. So that's the first step, the data. I need to know the data. But now the question is, given the data, what do I want to forecast? What are the measures of interest? So over here, I can have different objectives. So when we look at economic forecasting, when we read in the newspaper that inflation rate was 1% last year, what do we mean by? Or when we read that inflation rate is going to be 1% tomorrow, what do we mean by? So then here we have a collection of measures, and most likely what the economist was referring to with this very sarcastic comment was that if you focus your attention only on forecasting the conditional mean, there are many instances in which your exercise would be completely hopeless, because by the nature of the data, it's difficult to forecast a conditional behavior, right? So macro people are mostly interested in this measure, and by that, so then in order to establish notation, this omega is the information set. So with the information that I have up to yesterday, today I'm going to say something about this variable of interest, and I'm going to say my statement is on average. Whenever you read economic forecasting, there is always missing the measure that this forecaster wants to forecast. You never read something like, the average unemployment rate in 2016 will be, the word average disappears. So whenever we read economic forecasting, we never know what was the interest of the forecast. We assume, but we never know, right? But as I told you, if you look at the characteristics of the data, this, in some instances, this is not the measure of interest. If I'm working with financial data, I really want to know this, and this is a conditional variance. So again, what I'm doing is, in this case, forecasting what the volatility or the variance of this random variable would be given the information that I have up to time t minus 1. Well, sometimes I would be interested in forecasting extremes. So several months when I was here giving a seminar on interval data, the interest that I had in mind was to forecast a max and to forecast a mean value for a random variable. So that could be my interest. I don't have to focus on the mean. So if I have these extremes, I can have a good estimate of my range as an alternative to volatility, for instance. In some other instances, what I really want is just the sign. If I'm in the financial markets, now there are binary options in which the only forecast that you have to do is if the return of a given stock is going to be positive or negative. You don't have to focus on the value, you just have to focus on the sign. So then working with financial data, that could be my interest, the sign of a given random variable. If I'm working in an option trading desk, what I would like to forecast is the asymmetry of certain stock or the tail behavior of a certain stock. So now I'm looking at the third and fourth moments, and many people here are working on value at risk. So can I predict value at risk at the behavior of one of the tails, or other measures of risk that I have here, value in stress. This is a measure that I wrote about it a long time ago. And eventually, if I'm lucky enough, what I would really like to forecast, to have full information, would be the density forecast. If I have the density forecast, that is the last line over here, so what I'm doing is specifying all the distribution, all the potential events with the probability attached of a certain variable, given the information that I have up to time t minus 1. So what is the point that I want to bring? That when we do forecasting, and we need to specify what is our interest. And for most of what we read in the press, it's something that it must look something like this, like a central moment, but this central moment in many of the time series that we are working with is just, as I said, a hopeless exercise. So, I'm going to focus on the ideal. So then let me give you a representation of what is the ideal objective for a forecaster. And this is a plot from my textbook. So then what is this thing? So this is a stylized representation of what I want to go. So I have an information set up to time t. This is my time series, and I'm sitting here and I'm looking at the future h periods ahead. And with the information that I have up to time t, what I would like to do is to say something about this conditional probability density function, right? And when I say that this is my ideal, because if I have this ideal in my hand, then I can focus on the mean, I can focus on the upper tail or the lower tail, I can focus on the asymmetry of the density, I can focus on the sign above the mean or below the mean, right? So then all these measures that I gave you before are just subordinates to this ideal forecasting exercise that it would be to get the density forecast, right? So this is where we are going. So I'm gonna provide you with some exercises on density forecast and to give you some tools on how to evaluate the forecasting statistically with a statistical method. All right, so this is the introduction to the problem. So now, how do we reach this density forecast? Most of the people in this room reach this density forecast by the construction of models, right? So we have a model, and a model is a parsimonious representation of the information that we have up to time t. So I'm going to say some words about linear models versus nonlinear models to understand again the complexity of what we have ahead. A forecast is a complex exercise. So what is the workhorse of the forecasting? The benchmark, no matter how sophisticated you want to go in the building of your own models, the benchmark is always a linear model. So because we are talking about forecasting, this, all right. Am I going backwards? Okay, yeah. All right, so this is something very much known to the audience in this room. So we start with some Armand structure, and if we are lucky enough and we have some exogenous regressors, we can adapt to this Armand structure some regressors X, right? So then this has dynamics well specified. These regressors over here want to account for some economic story or economic structure that we may have. And then we have an error term for which we have to assume certain distributional assumptions. So then over here, I just assume some generic D with mean 0 if this conditional mean is well specified, and with some variance that it could be time dependent or it could be just a constant. All right. So then, if you use this benchmark to forecast financial data, the answer you know it. Good luck. Because there is not much that you can do. So then what is the paradigm in financial data if you want to model the conditional mean of this random variable? Well, this is the paradigm, a random walk with brief, and it's very difficult to improve upon it. What this thing says is that if you really believe in the efficient market hypothesis, then there is no sense to predict what is going to happen to the stock price of Google tomorrow, because the most that you can do is what has happened today. The rest is purely noise, is purely innovation, and by definition, an innovation cannot be forecast. So then this is the model that you will be working with, that in logs or without logs, that the information today is just the information tomorrow. Potentially there is a trend on the data, and the rest is noise. So what this can tell us is that if I go to the return, this is the first difference of the logs, then the best that I can do to predict this thing tomorrow is to give you the value of mu. And mu does not have any t associated with, so then this forecast is going to be a conditional and unconditional forecast because there is no time structure to exploit. And so the mu is just the historical average of returns, And if you are modeling indexes, this mu is very close to 0. This is the only exercise that you can do when you have financial data with this linear structure. However, we are economists, and as an economist, we cannot believe that we cannot forecast something that is so much based on the economic behavior of a given asset. So we are not happy with this random walk with grid. And then what we want to do is to say, I know economics. I need to bring economics into the modeling of this exercise, right? Well, I'm going to give you here 2 papers that they are very fundamental, or at least I don't know how many citations they have, because everybody's trying to replicate this study over and over and over. And because economists are so stubborn, we try to predict stock prices. So then this study by Welch and Moyal in 2008, it goes, I'm sorry, okay. This is one of the most cited papers in the financial econometrics literature, a comprehensive look at the empirical performance of equity premium prediction. The equity premium is defined as the total stock return, let's say the SP 500 monthly returns, minus the risk-free rate, right? And then this study was 5 years later replicated by Rapak and Zhu. And let me tell you what the story is about and what is the feeling that we have after using many hours of analysis on financial data. So then what the Welch and Moyal says, if this is the equity premium or the return, now the risk-free rate is basically 0, I need to understand the behavior of this as a function of whatever economics I understand on this financial data. So this is what is called a predictive regression, and you may be saying, okay, what is in this X? Just a minute. This model is again a linear model, but now the difference is that it brings economic structure into the picture, and all of us in this room know that if I have to estimate this model without an OLS estimation suffices. I don't have to be very sophisticated in my econometrics. So then what are these xt minus 1? So then they use this kind of 14 regressors if you want. I'm not going to go through all of them, but what you can see over here is that they are going to bring the intrinsic characteristics of the stocks or the financial and macro environment in which the stock is placed. So regressors 1 to 5, yes. These are characteristics of the stock that I'm modeling, like a dividend price or earnings price or dividend payout or the stock variance. So this is intrinsic to the stock. And then you say, well, and what happened with the market? Because there is this contagion effect, right? Well, the market is represented by the regressors from 6 to 14, and here you have you have treasury bill rates, bond yields, term spread, inflation, you name it, right? What do we learn? This is what the authors conclude. These models have predicted poorly in sample. Excuse me. Is the heat and the pollution on the bed. So, these models are predicted poorly in sample and out of sample for 30 years now. So imagine how stubborn the economies are. These models seem unstable, and these models would not have helped an investor with access only to available information to profit from the market. 5 years later, this author says that when recent studies provide using improved forecasting strategy, it seems that we can find some statistically and economically significant out-of-sample gains relative to this random walk hypothesis that we mentioned before. Okay? So then what are these people saying? Basically, these people, if you read the paper, what they are doing is trying to bring nonlinear features of these financial variables into the picture. So the word here, the move from 8 to 2013, is this word, nonlinear models. But now, if I want to characterize nonlinear models, this is a very, very wide exercise, because you can write nonlinearities as you wish. There is no class of nonlinear models. There are many classes of nonlinear models, right? So over here, how do we choose a nonlinear model? So what I want to tell you is a short story on how do we use the knowledge that is currently in the profession to model econometrically some time financial series. So I'm going to speak briefly about nonlinear models, and from that point on, we move towards this density forecast evaluation. So what do we mean by nonlinear models? When you look at the definition of nonlinearity, the definition is always done by exclusion. Anything that is not linear is a nonlinear model. So anything that is not, it does not have a normal representation, basically, is considered nonlinear. Well, let me give you an example of what we did some years back. So in this exercise, we are forecasting stock returns with some knowledge from economics. And what we are doing is basically exploiting a branch of what we call behavioral economics. And the idea here is that in our experience, whenever you buy a winner is the stock that is doing the best among a class of the stocks, right? The winner has a run for some time. And whenever you buy a loser, the loser is a loser for some time. So the question is, can we take advantage of this momentum on the upside and in the downside, such as a forecaster can get some advantage? So here, briefly, what we do is modeling a time series of returns in a cross-sectional and time-varying setting, understanding what is the cross-sectional position of a given stock in a given class. So you are at the very top, but you are at the very bottom. The top is the winner, the bottom is the loser. And then to understand what kind of dynamics we have to be concerned for a winner to go to the bottom and be a loser, or the loser freeze its run and going up and be a winner. So this is what we call a jump. So what we do over here is the joint modeling of the stock return with this jump moving from one category to the other. And now from here on is where the statistics start kicking in. So you have a bivariate density that is factorized into a conditional times a marginal. And then what we have to do from the modeling point of view is to model the dynamics of the jump. This is a duration analysis in action. And then we have to model the dynamics of the return, given that the jump happens. So what we hypothesize is that the dynamics when you are a winner are different from the dynamics when you are a loser. And the implication for that is that if now I want to forecast the return itself, then I have to face a mixture of densities, and the weight of each density is the probability of jumping from the winners to the losers, or vice versa, and the probability of not jumping, the 1 minus p. So what is this idea? This idea now, it gives you a forecast, a one-step ahead forecast of returns, but it is, as you can see, this is an example of a nonlinear model, because you have the mixture, you have conditional means on one hand, and you have this probability of jumping from the top to the bottom. Are these type of models working? Well, what we saw in this paper, just to look at this graph over here, is that this is an out-of-sample forecast from 2001 to 2005, before crisis. And what we do is this thick line over here, this is the accumulated return that we would obtain if every period of time I reshuffle my portfolio. At every moment in time, I look at my portfolio, I take a winner, I discard the losers, and I'm forming a portfolio of 5 stocks over time, in every period of time, doing this reshuffling. So this is what we get. This is a very nice number. At the bottom here, this dashed line is the buy and hold trading rule. That is, you buy the stock and you keep it forever. This is something that the small investor does very frequently, to buy and to leave it there for the next generations. So what we are showing here is that if you exploit anomalies, for a while you would be able to get returns. But you are not going to get these returns with a linear model. You have to think about which kind of feature or anomaly you want to exploit. Because eventually the anomaly will not be an anomaly anymore, right? Once we know it, everybody will do it. Okay. So this is just an example. So now, we have the data. We know the complexity of the features that we need to model. We have an objective to model. You choose any of these methods or any other method that you may have in your mind. You choose a model, thinking that whatever nonlinear model that you may have has to really beat the linear. Because if you don't beat the linear model, then you are doing a fruitless exercise. So the linear is always a benchmark, is always a good starting point for a forecaster. And then think if you can add some kind of nonlinear feature that can give you some advantage on the modeling that you are after. All right. So now where we are. We have the data, we have the model, and we use the model to extract a forecast, right? So I'm going to be so idealistic as to think that in fact you can extract the density forecast, this idea that we got after. So the question now is, how do I know if what I'm doing is statistically sound and is justified by the information contained in the data? So this is what we call the evaluation of the density forecast. What I'm going to present, I have 15 minutes or 20 minutes? Okay. Is to give you a sense of what I have been developing during the last 5 or 6 years with my graduate students. So what is this word that we call autocontour? What is this thing? Okay. So let me represent now a model in the most generic form, a model that economists use a lot. So then this is your time series, and it has a conditional mean behind, and it has an error. And here the error, I'm also interested many times in the conditional variance. So this is a heteroscedastic error, and I write the heteroscedasticity as the some IID innovation times the conditional standard deviation, right? So then this epsilon over here is purely an innovation, is IID. And the innovation now, it can be written as the time series minus the mean divided by the standard deviation. And what is the density forecast? The one step ahead density forecast is nothing else but this statement. Depending on the density that I assume for this innovation, this D, what I'm doing is making a claim that if I want to forecast one step ahead with the information that I have up to yesterday, this random variable, conditionally speaking, so a density forecast is a conditional density, it will have the functional form that I assume in this D, it will have this conditional mean, and it will have this conditional standard deviation. So this is clearly a statement on the density forecast produced by my model. So the question that we have ahead of us is, are you right? Because in this modeling exercise, you have to establish dynamics for mu, dynamics for sigma, and you have a clear assumption on the PDF of the innovation. Yeah? So what is the null hypothesis? The null hypothesis is that if this is true, the sequence that I would get after modeling, so then this epsilon, it would be an epsilon hat, but let's remove the estimation uncertainty for a moment to understand the null. So the null hypothesis, if in population this is my statement, the null hypothesis is that the multivariate density of this epsilon, what we have here, f epsilon 1, epsilon 2, epsilon t, if in fact these epsilons are IID, then what we have in the right-hand side is nothing else but the product of the marginals, right? And the marginal is well specified because I have here a statement on these marginals, right? So then what is this idea of autocontour? So what am I going to do with this null? How do I want to test it? The idea is as follows. I'm going to define a set of points. So out of this epsilon 1 to epsilon capital T, I'm going to pick up any two epsilons. So I start with the simplest case. And the only difference between the two epsilons is that they are far apart k periods. So then what I'm doing is choosing a set that we call it B, such as I get all this collection of epsilons with the restriction that when I look at the surface, then I have no more than alpha probability. So then this is the typical contour in statistics, right? You have, this is the bivariate density, and now you fix a value of your f, and you cut the density. And you cut the density horizontally, right? So then when you look at the plane down, you have contours of this type. Yeah? So then why do we call it autocontour? Because now what I'm going to plot is a bivariate density where in one axis I have epsilon t, and in the other axis I have epsilon t minus k. So that's the same process that the word auto coming into the contour. So let me give you here some shapes to warm up. So then if I assume that this innovation in my model, what is behind of this density forecast is normality, then the contours of a standard normal where epsilon t and epsilon t minus k are independent are these circles, right? This is what is under the null. If the epsilons were a student t, what I'm doing is epsilon t and epsilon t minus k are independent, so I have to have a product of marginal student t's, and when I do these autocontours, I have this kind of shapes, right? This is centered in the mean, in this case 0, remember the epsilons, right? And then the wider is the 99% contour, so there is 99% probability within that. The same thing goes here. Then we go 95, 80, blah, 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 up to, I think, 1%.
Yes, they are normal but not independent.
No, but this is not the null. I'm testing the null. Now I'm going into the testing. So I'm building surfaces that helps me with the null that I have established there.
You reject the null because it is not normal or they are not independent.
Exactly. So the null is a composite null where I'm testing the functional form of this innovation, B, and the dynamics, obviously, that I have specified in the conditional mean and conditional value.
Okay.
So it's a joint null.
Okay.
Okay? So then you have here the contours for student t. These are contours for exponentials, and this is the contour for Weevil. Okay? Under the assumption of independence. All right. So then, now the null is clear. Because if I have these contours for a given alpha, a given probability, now what am I going to do? Whatever contour I fix, the only thing that I have to do is to count how many points are falling into this contour. So this is the case, this is raw data for the index of the New York Stock Exchange, that is a very wide index, returns. So then basically I remove the mean, that is very close to 0, I divide by the unconditional standard deviation, no dynamics, assumption normality, and then the points that you see over here is just plotting the points of these standardized returns within the contours. If this is the 99% of the contour, how many points should I have outside? 1%, right? So then if I have 5,000 data, 1% is 50. So I have to have 50 points outside, and if I don't, something is wrong. Getting the intuition of it? Okay, very good. So then what am I doing now? Building this indicator. This indicator is what is going to tell me, are you in? Are you not? Are you in? Are you not? So in this case, I give a 1 whenever this couple is outside of the contour for a given alpha, and it's 0 whenever it's in. Yeah? So this is a counting process. Well, I'm not going to go into formulas, but where am I going? What I'm going now is to formulate a t-statistic that is going to check whether the proportion, so if I have here 50 over 5,000, if this 1% is satisfying the data. So then the p hat is the sample proportion, and under the null, it shouldn't be very far from the theoretical alpha that I have chosen. Yeah? So then this is a t-statistic that is going to tell me whether, if I have instead of 50, I have 51 or 52 or 55, whether this deviation is statistically significant or it's not. A very simple t-test on the indicator that I just built, right? And this indicator is for a given k, epsilon t minus k, and for a given alpha, that is the subindex I, right? So then, now if you move the k's, this graph sounds familiar to you. Because now what I'm plotting here is the value of the t-statistics for different k's for a given I, right? So this graph is going to help me to understand if I reject the null, if I have deviations from dependence. This is the graph that we're going to use from dependence, okay? All right, now, no more formulas. What I want to say is that if you have a t for a fixed k and for a fixed alpha, now you can build up umbrella tests, moving the k's or moving the other contours, right? And then this is what I have here with not much explanation, that I can build up a chi-square whenever I fix a contour for many lags, or I can build up a chi-square when I fix a k and I move over all the density surface. Okay? Application. I'm going to show you an autoregressive conditional duration. This is a model that it was in the literature since 1998. What we are going to do is to see if this specification that is in the paper is justified by the data applying this autocontour test. So over here, duration is the time that passes between any two trading transactions, right? And the duration is specified in this multiplicative form. So this psi I is the conditional duration, expected duration, excuse me. And this innovation epsilon is the one that it has to be IID with a given density. In this particular case, the densities that they are most popular are exponential and Weibull. And let's see, then in the paper we have another one. But let's see if this is satisfied by the data. All right, so then I'm not going to show you numbers of the test. I'm going to give you the graphs, and you would be the judge. So then what is this thing? This is, durations is a strictly positive quantity. In the first graph, this is just no model. No modeling at all. So then this is just the data, standardized, and these are, can you see the colors here? More or less. So this is the 99%, 95, and we go down up to reaching very small contours, right? Well, the data is completely out. So then the raw data is not conditional exponential. That is the easiest assumption that we can have. So then what do we have here? Let's model the dependence. If we model the dependence, this is what we got. Can you see how the model helps us? The tests are telling you, you are in the right direction. You are picking up the dependence in this conditional duration, right? But the question is, how many of these points we have outside of the 99%? So the model helps us to bring the data where it should be, contained within these autocontours, but the number that we count outside of the 99, or outside of the 95, or outside of the 80 is more than the theoretical value that we should expect if we had the case that the model and the density are well specified. So then over here you said, all right, exponential is not going to make it. This is an assumption. So let me see if I do Weevil. If I do Weevil, then can you see the contours now, they have certain curvature, and the curvature help us to bring some of these observations in. So the tests are telling me that, yes, you are going into the right direction. You need something stronger than exponential. Exponential does not allow for overdispersion in the data. This is quite strict for the qualities of the data that I have. So I have to go to something more flexible like Weevil. The problem, and then this final one is Burr, that it has also this curvature, but this doesn't seem to do as good as a job as the Weevil. The problem with the Weevil, though, is that when we count, something that you cannot see, when we count the very small durations, when there is high frequency trading, then the Weevil assigns a lot of probability compared to the compared with what we find in the data. So the bottom line of this exercise is that if you are working in autoregressive conditional models, we understand very well the behavior of large durations. So there is a lot of time passing from one structure to the next, but we do not understand yet, we don't have a parametric density within the class of parametric densities that we know, that models, I don't want to say perfectly, statistically perfectly, what we call the small durations. We don't have this density yet, okay? And that is something that we learn from this autocontour test. All right, so what I saw...
Have you tried this test for Garch model?
Yeah.
When the assumption of the Garch model, different Garch model is quite important.
The student works pretty well. I think going further than the student
using GJR or just a Garch or iGarch is important also.
You mean distributional assumptions?
Yeah, these are the variance assumptions.
The dynamics we are pretty happy with. I mean, I think what we are doing is just more and more sophisticated models, and the addition of knowledge is minimal.
Yeah.
And with densities, for indexes, a student does it. If you go to particular stocks, then you may have better refinements. But for aggregate stock indices, a student does it very well. And you may say, well, it's 5 degrees of freedom, or 6 or 7, but in this ballpark. Okay? Okay, so then what I showed you is the first generations of tests. Now we have a second generation, but in the time that I have, it's going to be very brief. And Federico, I'm not going to be able even to read what you just read. But let me give you, what is now this generalized autocontour? Well, the problem that we have is that these autocontours that I showed you before, they are very nicely pictured because we can get analytical formulas, right? But the problem is that there are densities, mainly when you go towards the multivariate modeling, for which these formulas are not that easy to get. And then, if you don't have the autocontour, you don't have the test. So then we have to think in a way to generalize the test, such as no matter the density that you have behind, no matter the nonlinearities that you have behind, no matter what the forecaster is hitting as a wall, you can really overcome. So what is this thing? So this generalized autocontour is a statement, or is basically the same methodology, but on what is called the probability integral transform. And what is this? This is a very old concept that it comes in the statistical literature since Fisher, then Rosenblatt used it, and then Diebel and company brought it into the economics field. And what the PIT is nothing else to get the, okay, let me start just 1 second to establish notation. So this statement that I have here with the star.
La flecha.
Esta.
No, escribe. Left. Okay.
All right. And I don't want to run. Okay, so then this F star is this density model that we spoke about a minute ago. This is my density model, the statement that I have on this conditional density. And now what I'm going to do is, using this modeling, over here I have a lot of modeling. I have the mean, the variance, the density, all the modeling is contained in this notation. Using this modeling, I'm going to integrate for all the values that I have in my data to obtain, you are integrating a density, so you have to get a number between 0 and 1, right? The trick over here is that if in fact this is the true density, this number, the PITs, the probability integral transform, has to be uniformly distributed, and it has to be IID. And that's the beauty of it. That now, in the first generation of the autocontour test, I have IID standardized errors, or residuals after destination. But now what I'm going to have here is, after destination, I'm going to have IID PITs, right? So then the null hypothesis of testing whether my density is correctly specified, density forecast, translates into testing the sequence of PITs that I would get, satisfying this particular property, that is IIDness uniform 0, 1. So now the question is, how do we bring the autocontour to that? Because imagine, this is a uniform between 0 and 1, right? So then you have a random variable 0, 1, the other one 0, 1, and what is the structure? The structure is a cube, right? 1 by 1 by 1, cut it, as I did before. What do you get? You get always a square 1 by 1, right? So then the autocontour does not exist, basically. So then what we do is, instead of cutting the density, okay, instead of cutting the density now, I'm going to cut the domain. So now I'm going to define this generalized autocontour as the collection of PITs far apart k period, such as this guy and this guy has a bound that I fix because I want to see how much probability is on it. That, and what you say, why you have this square root of alpha I? Well, look at this. Oh my gosh.
That's the screen below, right?
Okay. I need technical assistance. Okay, go, help me out with from there. Go. Here, just here, this one. Okay, so now look how do we retrieve the autocontour in the univariate case. This is a PIT at time t, PIT at time t minus k, and now what I'm going to do is I'm going to fix boundaries such as I control the probability that it goes into these squares. I can do the cutting in many other ways, but I have chosen this symmetric cut, right? So then I'm going to look at the points that they are within this square, right? And if my model density forecast is well specified, then I have to have in this particular, with these particular boundaries, 16% of the probability mass, right? We have the generalization to the multivariate case that I'm not going to enter into because I want to give you just the idea of what we do. So now you keep on cutting these guys, and what we are going to do is to place our data, our PITs, on these squares, and to make sure that it's uniform and is IID. So if this is the case, what is your expectation? That you are going to have points all over, because are uniformly distributed, right? And not only, but I have to have 16% of the probability mass. If any of these two things fails, then I reject the null. Yeah? So it's the same idea of autocontour, but instead of cutting in the generalized error, I'm cutting in the probability integral transform behavior. Right? Go.
No.
Down. I mean, the next one. Okay, so then, now the construction of the indicator is the same. Are you really, this is an indicator, are you really into this picture or you are out? Again, a series of 1 and 0s. And by the same token, I can build up a t-statistic and whatever portmanteau test I want, chi-square test. Let's go to the application. Just, let's keep on moving more.
I think you can use the pointer, Gloria.
Yeah? Oh, yeah, okay. All right, so then let me give you an application to finish up things. So here, what do we have? Now we have modeled the contemporaneous correlation of trading activity in the 3 major banks in the United States, in Bank of America, Wells Fargo, and JP Morgan, right? And this issue of trading activity is really related to issues of liquidity, right? And some of the feature of this financial crisis is that at some points the market was very liquid. Nobody could trade anything, right? So then the question that we have over here is it true that the correlation between any two organizations, any institutions, is constant over time, changes over time? What is it? How do we model it? So then what you have over here is we are going after the conditional mean. This is the number of transactions per institution, and it's a trivariate system in this particular case, and we can assume for every bank a marginal behavior that in our case is either Poisson or negative binomial, and then the question is, are these institutions contemporaneous correlated or they are not? So when we go through this exercise, I'm going to show you pictures again. So there is a lot of modeling behind this conditional mean, right? And now what I'm doing is bringing the PITs of the 3 banks, in this case at time t. So then I can observe any other lag, but because I'm going towards the question of contemporaneous correlation, so I have the assumption of a Poisson model in the marginal, and I place my PITs in these cubes. This little cube red here should have 10% of the observations. The blue goes up to 80%, and the green goes up to 100%. Okay? So then these are 3 hyperplanes, basically, because we are now multivariate, with theoretically a given amount of probability mass. Right? If you see this plot, you say, this model is very wrong. There is no uniformity here, right? All the observations are going to the edges. They go to the boundaries. They don't have a place in this volume, right? So Poisson model, gone. What happens if I assume a negative binomial, that is a more flexible density? This is the PIT's location. What do you see over here? Much better than this one. But what do you see? There is a tendency for the points to really move along this elliptical behavior, right? So the negative binomial is better, but it's not getting all the features of the data. It seems that we have to go, this is no contemporaneous correlation. So then how am I going to bring the contemporaneous correlation? Well, here it is. It's not here. All right. So what we are going to do is to get negative binomial marginals and to model the trivariate correlations with copulas. And the copulas that we are dealing with, or we dealt in this paper, is the Gaussian copula. You see this kind of asymmetry because the marginals are negative binomial, right? If you have marginals that they are normal, then all these things would be circles again, right? This is the inverse Gumbel, this is the Clayton copula, and this is a mixture of these two. So what I want to say over here is that it seems to us that what the model is telling us is that when the trading, when the number of transactions is very small, I have a lot of dependence. This is a matter of correlation, right? But when I go towards larger volume, when I trade a lot of number of transactions, what happens with the correlation? The correlation is much loose. So the question that I had at the beginning, are these things correlated, these banks correlated? You can say yes if the market is very thin, no if the market is very thick, a lot of transactions, right? Is this justified? These are my cubes again. Yes, I'm cutting. So the bottom line over here is that the Gaussian copula is not going to do it for us because we have an accumulation of points at the very top, right? Over here, if this is uniformly distributed, you should have a much lighter picture. We get it here with the Clayton copula, right? This is a much better picture than this one. This is in between because still we have a big concentration in the upper of the contours, right? But on the other hand, the blue dots are more spread out. Over here, it seems that they are more compact, right? So then either model would do it much better than the Gaussian copula. And what we did finally, because the problem is here in this case, and the problem is here in this case. So what we go is to a mixture of both with different weights, such as we lighten up the upper, as you see here, and we stretch somehow the blue a little bit over here, and this is the model that we propose. Okay? So why do we propose this model? Because the autocontour tests guide us to do so. And of course, behind this picture, there are a lot of numbers on this test, right? But the pictures is a very intuitive way to help you in the modeling process. So I'll give you just a sense of how you can use this test. And the third generation is to use this type of test to detect breakpoints in the series. And this is the paper that Federico was reading. So basically, just to finish up, what we have now is a collection of t-tests. I'm going to speak only about the t-test. So you have your prediction sample, and you are applying your test to, say, the very first 100 observations, right? And you get a test from there. Now you move to 101, but again 100. Discard the first 101, a rolling, and get another t-test. Now you move to 102 and get another t-test, and so on and so forth. So if you were to plot all these t-tests, you would have a plot like this. This is the Phillips curve, and this is the t-test for the 99% autocontour. So the model of a Phillips curve, linear model, is doing pretty well up to this point. And then over here there is some jump, and then over here there is some jump. So then this type of test has helped us to detect a rejection of the linear Phillips curves in what we call the Great Moderation in the United States, plus the beginning of the financial crisis. So the linear Phillips curve really breaks during this time. How do we get it? Through the behavior of the T's over time with this growing period. So anyways, I'm going to finish over here. So what I want to say, probably you don't need much convincing, but financial forecasting, economic forecasting is difficult, isn't it? It's difficult. So then what do we need to do as forecasters? What we need to do is really to have an open mind and be ready. And be ready for what? we need to expect the unexpected if we want to keep abreast with our knowledge of forecasting. And this is not just said by me, by a person much wiser than me, Oscar Wilde, in 1895. So then, even then, forecasting was difficult, no? So I close just with this wise thought.
Can we have this the code, is it MATLAB, is it R, or?
Yeah, we provide the code freely. It's written in MATLAB. It's very easy to run because this is a counting process. Yes. Anyone who wants it. I don't think that you're going to have much to discuss because I didn't. So then probably what you saw is this, right?
But I actually have a comment on your first slide.
Okay.
You just divided macroeconomics and financial, let's say, concepts.
Yes.
But there's something in between, and it touched my heart a bit. It's, let's say, fiscal finance or financial fiscal data.
Like? Give me an
like,
example.
I don't know, VAT revenues. What's the issue? I mean, sometimes it has certain elements on the left-hand side, and sometimes it has certain elements on the right-hand side. For example, if you would like to forecast VAT revenues, sometimes you have, first of all, you have the noise of the government. I mean, you never know if the government is going to take a measure or not.
Yeah.
And the other thing is that you have this annoying difference between accrual and cash data that always bothers a lot. But actually, I found a third use of your, let's say, auto contours, or I would say something in forecasting which is really difficult, and it's actually communicating the results. So usually one of my most difficult tasks at work is explaining my boss why the GDP forecast fell by 1% from last month to the next one, to this month, because, I don't know, we changed one of these parameters in the model because we realized that adding one more, let's say, observation changes, I don't know, the intercept. And actually, this gives you a very easy way to communicate this.
Exactly.
And also, sometimes when you have to, let's call it endorse forecasts of other people, if I would be able to plot, let's say, either the errors or relative to any benchmark, for example, you can take the consensus forecast, or I think for the US you also have it. So then you can see, you would be able to see how the government, let's say, compares or ranks to the rest of the profession. And it's actually difficult to explain. And if you would have it in a square or in a cube, I would say that a journalist would understand it.
Exactly. So the point that I made at the beginning is that when you read the economic forecasting, it's always a number with no context whatsoever. Because they are not telling you what they are trying to forecast, right? They are not telling you what kind of uncertainty these people are facing. And it seems that the forecasters have really a bad rap because we never hit the point that it was. Yeah? So then, what you need to tell to your boss, if he's not an econometrician or a forecaster, is that you are doing this. And that obviously you would like to get this expected value that is the most central value to your forecasting exercise. But if you get a forecast over here, or a forecast over here, this is not a bad forecast. The only thing is that it has certain probability, right? So then, if you have to aim for something, no matter the time series that you have, it is for this thing, the density forecast. And get your hands wet. You have to make an assumption on what this density you want here, right? And then you can put within your model, you can overlap the models of others and see where are the differences in these densities. Where do you have a common area? Because if all of you agree on this with a probability of whatever, then you are in business. And the fact that instead of being 2.5 is 2.3 is irrelevant. because we know when we do a forecasting exercise that the probability of being wrong is 100%. But wrong in which sense? That I'm not going to hit exactly the value that is going to happen in the future, because what I'm modeling is a random variable. Yeah?
And the other thing is that how, let's put it this way, how sensitive the results are when you have maybe a bit less observations. Because you made you made in your paper, the one I read, and I think the sample was 300 100 observation, 150 the
minimum, yes, if you look at the generation of papers, we have tried different samples in our Monte Carlos. The smallest samples that we got is between 100 and 300, because the contours are very sensitive in the stream, right? Imagine that you have a time series of 50 observations. What is 1% of 50 observations? 0.4. Yeah. So then what happened with this indicator? The indicator varies between 1 and 0, right? So then, in a sample, it's very likely that at the very extremes, the indicator is not going to have any variability. That you have all zeros, nothing is there, right? So then, these results, the statistical results are all asymptotic, so large samples, right? And the Monte Carlos, in which we have small samples, then obviously for 50, you cannot do well at the extremes, but you can do very well in the middle.
You could always cut it less times.
Exactly, because you control the contours that you want to check. For those of you who are working in value at risk, you want only one tail. So you don't want the central contours. You want to see what happened at the very extremes, right? So this is one of the advantages of this methodology, that you fix the area of this density that is interest to you. For the VAT revenues, you really want to be in the middle, right? But you have to have a sense of how wide this density is in order to sell your forecast. Yeah?
¿Any more question?
¿Se puede en español?
Sí, podemos hablar en español. Sí, es verdad.
En inglés no está bien pronunciado. Entonces. Es más fácil pronosticar después de la crisis, porque hay ciertos productos que contagiaron todo, ¿no?
Sí.
Entonces ahora cuando cae China, caen todos. Cae Brasil, caen todos.
The answer is depends on what you want to forecast. I mean, if you want to forecast interest rates, now it's very, very difficult. Why? Because there is no variability. I mean, we are in the lower bound, right? Bueno, estamos en el lower bound.
Never knows.
No, pero lo que quiero decir es que estoy cambiando lo que quiero decir es que para producir un forecast bueno, intrínsecamente tienes que tener variabilidad, right? Entonces, la predicción de interest rates, si me la pides mañana, yo es que no me voy a preocupar de esto, porque te voy a decir lo mismo que hoy, ¿no? Porque una vez que llegas al cero, a no ser que seas el Banco de Japón, que te vayas a un interés negativo, pero si estás en Europa o estás en Estados Unidos, dices el 0,25 y no lo cambio. O sea, esa es la manera más fácil de hacer una predicción cuando las cosas no se mueven, ¿vale? Pero para hacer una predicción en la que la estadística te ayude, el elemento esencial de cualquier ejercicio estadístico es la variabilidad de tu muestra, ¿no? Porque lo que tenemos que pensar es que tenemos en el futuro, para nosotros económetras, el futuro es una variable aleatoria, ¿vale? Entonces, si es muy estrechita, muy alrededor de la media, pues es que no me preocupa de estas cosas. Pero si empieza a tener variabilidad, ahora es cuando las cosas se ponen interesantes. ¿Cuál es my value of risk? ¿What is la media? ¿Cuál es la varianza?
Tengo otra pregunta que no está relacionada con el autocontour, pero me surgió durante el paper ese del 2008.
Sí.
Los datos, o sea, cuando se publicó, ¿has probado replicarlo hasta ahora?
¿Cuál?
El
no linear model.
No, el que nos diste un ejemplo para... sí, exactamente, de lo que es un ejemplo de no linear model.
Sí.
Si eso lo leyeron los 10 fondos más grandes o lo que fuere,
Sí.
básicamente empezaron a tener esas estrategias.
Sí. Dos cosas. La primera vez que presenté ese papel fue en la Universidad de Chicago, en un MBR workshop. Recibí un montón de requests de peticiones de bancos, muchísimas. El estudiante graduado que estaba en ese momento trabajando conmigo, Santosh Mishra, empezó con un trabajo académico y ya no está en la academia. Entonces sí, hubo un momento en que eso la anomalía era anomalía y no lo he replicado últimamente porque es un trabajo inmenso, porque trabajábamos con los 500 componentes del SP500. O sea, el modeling exercise que tuvimos ahí pues llenó la tesis de Santosh porque era un trabajo súper intensivo, ¿no? Pero que bueno...
ha destruido todas las oportunidades de arbitraje que había.
Bueno, pero el ejemplo que yo os doy es que si aprovechas lo que se oye en la profesión sobre qué tipo de anomalías hay en el mercado, nosotros como Statistical o económicas decimos, ¿cómo puedo plasmar eso en un modelo del cual pueda extraer, pues en este caso, lo que quiere es la predicción del return, ¿no?
Seguramente esto no sé si la experiencia te lleva a pensar que puede haber cambios en las densidades,
sí.
Sobre todo en datos financieros, ¿no? Es posible que en periodo de crisis haya una densidad más pesada en las pruebas.
Sí, de hecho,
estos test no están diseñados para detectar esto, ¿no? Sí.
Claro, sí, te van a rechazar cualquier hipótesis que tengas. O sea, tú puedes empezar con una hipótesis de que tienes una mixtura de normales. Por ejemplo, todos los Markov switching models, ¿no? Los habéis aplicado, te están diciendo que es una mezcla de normales en recesión y en, ¿cómo es lo he puesto? Recesión. Expansión, y en expansión, ¿no? Y entonces tú predices una media cuando estás en expansión y predices otra con cierta probabilidad cuando estás en
hablando más de la densidad, me estás hablando, claro, de la media o la...
Claro, pero
estoy hablando más del shape, de la distribución.
¿Del shape de la distribución?
Sí, siempre una Student o una gaussiana.
Claro, pues exactamente es lo que este último papel está haciendo, tratando de averiguar dónde los datos se vuelven inestables. Y la inestabilidad se puede entender como una ruptura de las dinámicas de la media o de la varianza o ruptura de la densidad, ¿no? E incluso si tienes la misma functional form de la densidad, si te cambia el modelaje de la media y el modelaje de la varianza, pues ya tienes una densidad distinta, ¿no? Que puede ser más estrechita, o puede ser más ancha, o puede estar desfasada hacia un lado o desfasada hacia otro, ¿no? O sea, esto es la ventaja de estos test, que tú formulas lo que crees está pasando ahora y el test te va a decir, vas mal, ¿no? Y además...
Bueno, claro, pero hacías un algoritmo window, ¿no? El último test es...
Claro, exactamente. Entonces vas moviendo la muestra, un dato detrás... Claro, y entonces cada vez...
Te va diciendo
cuándo el test se comporta y cuándo no se comporta, ¿no? Y entonces para la Fields Curve, que es una curva que trae de cabeza a todos los bancos centrales, pues lo que ves es que efectivamente en la Great Moderation, donde nada se movía, pues el modelo de la Fields Curve no existía, no había un trade-off entre inflación y empleo.
Sí. Pregunta sobre las compras, porque estoy leyendo.
Sí.
Hasta ahora todavía no me creo mucho, pero una tema es para hacer cómpulas finas.
Sí.
En principio, todas las distribuciones marginales debería ser continuo. Porque yo veo lo de la diapositiva que pasó, o que la negativa, en principio está en...
Un punto muy bueno, y ese punto lo trajo al referir para este paper, efectivamente. Y seguimos poniendo... y seguimos con este ejemplo de Trading Activity. Lo que nos salvó en este caso es que el número de trades es muy grande y entonces se podría considerar la variable casi continua. Pero si tuvieras el número de transacciones 1, 2, 5, 6, 7, Entonces, tu punto exactamente está en la crítica de este papel, que la cópula se tiene que adaptar a una variable discreta. Buen punto. Sí.
Una última pregunta, ¿vale? Luego sí, para terminar.
Sí.
¿No daría información de una estimación bayesiana, por ejemplo, para que uno pudiera tener una posterioridad de un modelo?
Sí, sí, sí.
Un modelo y decir, bueno, pues esta es la distribución, pero yo puedo extraer elementos que creo que pertenecen al modelo verdadero,
Sí,
que
sí.
seamos puede acercarnos a él.
Sí.
Y que por lo tanto a partir de ahí uno pueda decir, bueno, pues esto se parece más a este tipo de distribución, a lo que
Sí.
Sí, ¿no aportaría un científico bayesiano a esto? ¿O que nos ahorraría
bueno.
muchos contrastes de hipótesis anteriores?
¿Cómo se dice? Disclaimer. No sé nada de bayesiano. Por decirlo de alguna manera. Pero este test, aunque está dentro de la estadística clásica, si tú realmente después de tu estimación bayesiana tú tienes una posterior, la posterior está bien definida en términos de forma funcional y los momentos que tengas en ella, ¿no? Pues siempre podrías hacer un autocontour de esa posterior y ver si esa posterior está justificada.
Esa posterior puede ser cualquier distribución no conocida.
Claro, no, pero si no tienes functional form, no tienes que ir a... Tienes que ir a una numérica, ¿no? Una non-parametric. Pero de una non-parametric también puedes conseguir la probability integral transform. ¿Puedes?
Sí, sí.
Pues ahí lo tienes. En la segunda generación de testes, tú coges las PLTs de esa posterior y tienen que satisfacer el placement, ¿no?, de los puntos en esos cuadrados que te he puesto. Y eso sería, claro, ahora el test es clásico. Yo no sé si en tu... De la manera que tú piensas puedes combinar una estimación bayesiana con un test clásico, ¿no?
Y la pregunta que quería hacer es, todo esto no se habla nada para este test de la hipótesis alternativa. Estamos pensando que
Claro, sí, esto es como una especie de portmanteau test que tienes, ¿no? Donde cuando rechazas no caes en una alternativa dada. Y tú puedes decir, bueno, eso tiene que tener consecuencias para la potencia del test, ¿no? For power. En estos papers que te he comentado tenemos simulaciones extensivas sobre el power, ¿no? Entonces tú la alternativa nunca la conoces. Nosotros a través de simulaciones cogemos alternativas que se desvíen muchísimo y muy poco de la nula, y el resultado en general es que son test muy poderosos. Y el primer papel que publicamos, el referí nos dijo que había que comparar con los test de no sé qué, no sé cuántos y tal. Nos hicimos un repaso de la literatura y cogimos los test más poderosos, que tenían más potencia en ese momento, que es un papel by Hong and Lee, y implementamos sus tests y todavía les ganamos a ellos. O sea que si quieres ver cuál es la performance de estos tests en términos de potencia, te recomiendo los dos primeros papers, el que se publicó en el GBS y el que se publicó en el International.
Bueno, pues muchas gracias a todos por venir. A Gloria por la maravillosa presentación. Ha sido un lujo tenerte aquí y bueno, pues...
Gracias. Sí, ya
está, se han estado los de marzo, porque a lo mejor se deja atracar o alguno que tenga interés en hablar con ella.
No, sí, la verdad estoy de base en la Carlos III, en el Departamento de Estadística, pero tengo un coche y...
Bueno, el que tenga interés también puede
quiero decir que si os apetece comentar algo que estéis haciendo de tesis o de trabajo y tal, pues estoy a un paso, vamos. Sí, estoy ahí en la red.
La forma de encontrarla es poner Gloria González Rivera en Google y vais a encontrar rápidamente.
Sí, mi email es gloria.gonzalez@UCR, University California Riverside.edu. Bueno, pues muchas gracias por vuestra atención.
Gracias.
Que no se me olvide mi flash drive, que yo voy a
Llamarán a mí o a ti. Pero, Gloria, te puedo decir que sí, no me ubico mucho en Madrid, vivo todavía. Un poco porque tenemos varias cosas dando vueltas y la verdad es que está muy interesante. Yo le mandé tu paper a uno de mis compañeros más, digamos, que trabaja más en este tema, creo que se lo estaba viendo y le comenté y yo no sabía que era
Sí. Tengo un calendario muy apretado, lo que se manda es muy difícil. Entonces te digo las fechas que tienes más libre, esta mañana o tarde.
Los 5 estos, yo no sé cómo se viene.
Yo vivo en el espacio de esa colección. Vosotros estáis como en la castellana hacia arriba, de la misma manera que cojo un coche para irme a casa y lo cogen, voy a vosotros y me paso una mañana como así que es porque me mandan un email y ya